Today we're going to talk about inverse functions, and here we go. So the first topic is what's the difference between an inverse relation and an inverse function. So remember that not all relations are functions. Not all relations are functions, but all functions are relations. Clearly I'm asleep at the end of the day as I'm doing this. So again, not all relations are functions, but all functions are relations. So an inverse relation just means the set of ordered pairs created when the ordered pairs of the original function are reversed. So let's go ahead and write an original function. So my original function is 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's my original function, and I know it's a function because, and actually it's just a relation. It's a relation because it's a list of ordered pairs. This also happens to be a function because none of the x values repeat. So to get an inverse relation, we're just going to switch the x and y value. That's it. So let's label this one as a relation. So I'm going to just abbreviate it as well. And then the next one's going to be inverse, so INV relation. Then we'll determine, is the inverse relation a function? So we're going to go ahead and flip these around. So instead of 1, 2, we've got 2, 1, 4, 3, 6, 5, 8, 7. So as you look at this inverse relation, look at the x value. The x doesn't repeat, so it also happens to be a function. So yes, function. Yes, function. Right? So an inverse function is, so this inverse relation also happens to be a function. Not all inverses are functions. So again, you still have to look at the x value to see if that x value repeats. So look over here. This is just another way to show a relation. This is called a mapping. So this relation and its inverse. So in a mapping, the domain, remember, are the x values, the range are the y values. So I'm going to create the set of ordered pairs from this mapping. And so the mapping just means you're going to map 1.2 onto 1. It creates an ordered pair. So notice the arrow always goes from left to right. So I'm going to create the ordered pair 1.2, comma 1. So this is the relation R. And the first ordered pair is 1.2, comma 1. Oh, that's a terrible one. Let's try that again. 0.21, comma. And then the next ordered pair goes from 1.4 to 1. And the next ordered pair goes from 1.6 to 2. And finally, I've got 1.9 to 2. So let's look at the inverse. So if I switch the x and y's, and that's what they've done here, so the domain here has become the range, and the range here has become the domain. Notice now that instead of 2 arrows coming towards the 1, the 2 arrows are leaving the 1. And so the inverse relation R is, I'm just going to switch the x and y values. So I get 1, comma 1.2, 1, comma 1.4, 2, comma 1.6, and 2, comma 1.9. So as you can see, relation R, look at the x value, 1, 1, 1.2, 1.4, 1.6, 1.9. The x value does not repeat. So that means that this is indeed a function. So this is a function. The x value doesn't repeat. But now look at its inverse. 1, 1, there that x value repeats. So I'm going to underline those. So you've got 1 and 1. But you also have 2 and 2. But it doesn't matter because as soon as I saw the 1 and the 1, immediately this is not a function. So this is not a function. So here's an example of a relation that is a function, just like the previous one, but its inverse turns out to not be a function. And also, when you look at the mapping, anytime you see 2 arrows or more than 1 arrow leaving a domain and going to a range, it's definitely not going to be a function. All right, so finding the inverse of a relation. So let's make this bigger. There we go. So to find the inverse of relation S, we're just going to switch the x and y. So it's pretty simple. We're going to have x and y. So instead of, I'm just going to swap the x and y. So my x is now becoming -1, 0, 1, and 1. And my y is going to become 1, 2, 3, and 4. So now, and let me label this as the inverse relation S. So now as you look at this, the original relation, if you look at the x values, they don't repeat. So this is a function. But on the inverse, if you look at the x values, right there, they repeat. So because of these values right here, this is not a function. Okay, so that's pretty simple. Now we're going to look at a graph and apply a new test. So yesterday or day before, we had talked about the vertical line test to determine if a graph is a function. So if I applied a vertical line through a graph, and if my vertical line didn't touch the graph more than once, it was a function. So this first one, this first relation, this graph is a function. Same thing with this one. As I put my vertical line through this graph, no matter where I put it, my vertical line only touches it once. So both of these graphs, as they are considered functions. Now, we can apply this horizontal line test. It makes sense that in an inverse, if I switch x and y's, that I would switch a vertical line to a horizontal line in order to test my inverse. So if any horizontal line passes through more than one point on the graph of a relation, the inverse relation is not a function. So look at the first one. So now I haven't even graphed the inverse, but I don't need to graph the inverse in order to determine if the inverse of this function here is a function, because I'm just going to apply the horizontal line test. So you can see here that they've drawn a horizontal line through this graph. And as it goes through this graph, it only touches the graph once right here. Here's another place that you could put the horizontal line. It touches that graph only once right there. So it doesn't matter where I put my horizontal line, no matter where, it's only going to touch this graph once. So this inverse is a function. But look at this one. Remember, this graph here was a function because it passed the vertical line test. But as I pass this line, this horizontal line through it, it's touching the graph here and here. So if we switch the x's and the y's on this graph and try to graph them, you're going to end up with some graph that looks like this, and it's not going to pass the vertical line test, therefore it's not a function. So instead of having to graph it to figure that out, we're applying this horizontal line test. And again, no matter where you put it, unless you put your line right here, that's the only place where it would touch it once, it's going to touch it twice. So the inverse of this graph is not going to be a function. Now, you don't have to start off with a function in order to test the inverse for a function. You could start off with a non-function and its inverse could be a function. For instance, I'm going to draw a graph. Let's draw a sideways parabola. Then if I apply, now you would agree that if I ran a vertical line through this graph, it's going to touch it twice, here, here. And so this graph is not a function. So, original graph not a function. Now, I'm going to apply the horizontal line test. So if I ran a horizontal line through this graph, notice it's only touched it once. Once. No matter where I put this horizontal line, it will always only touch it once. So the inverse graph is a function because it passes the horizontal line test. So you can start off with a graph that is not a function and its inverse becomes a function. You can start off with a graph that is a function and its inverse is not a function. You could also start off with a graph that is a function and its inverse is a function. And you can start off with a graph that's not a function and its inverse is also not a function. So there's all kinds of different combinations that you can have. All right, so this is your time to determine, by using the horizontal line test, whether the inverse of each relation is a function. So go ahead and label this blue line A, because it's missing its label. And what you're going to have to do is ignore the fact that this red line is here. You're going to test this A line as if the red line's not here. And then you'll test the red line, which is B, as if the A line is not here. So apply your horizontal line test, and so pause the video, apply your horizontal line test, and then restart the video to see if you're correct. Okay, so as we're looking at A, well, I guess that was there the whole time. I wasn't really paying attention. But as we're looking at A, so right here, I'm only looking at this. If I apply a vertical line test, it is not a function. But if I apply a horizontal line test through that blue line, it only ever touches the blue line once, no matter where I put this horizontal line through it. So the inverse is a function because no horizontal line passes through 2 points on the graph or more, right? So then let's look at this. So I'm going to go to another slide. So for B, again, if I apply the vertical line test, this time B is a function when I apply the vertical line test. But it looks like here that the inverse is a function until you get right through here. You're hitting it once, twice, 3 times. So it doesn't matter that down here it only hits it once. It just takes one instance. And there's actually multiple instances through here that I could run through. So the inverse is not a function because a horizontal line passes through more than 1 point on the graph. Composition of inverse functions. So now we are going to use our knowledge of compositions from the previous video and inverse functions. So this is just new notation for you that says if I use, write it here, if I use f to the -1, it's a -1, of x, I'm asking for the inverse function of x. So I'm asking you to change the x and the y. So you're going to learn how to do that today. And this is just a composition. So if we take the inverse function and substitute the original function into the inverse and get x, an interesting thing occurs if you switch it around. If we take the function and substitute the inverse function into the original function and get x, if both the composition and its vice versa composition, isn't this vice versa, if they both become x, then I know that those functions are inverses. That's all that this property is saying. So let's go ahead and apply it. So if the and this is just what the words are saying of that property, if the compositions of two functions equal the input value, the functions are inverses. So if I have two functions, so over here you have two functions, 3x and 1/3 x. If I do f of g of x and then g of f of x, if their answers, those compositions, turn out to be just x, then the functions are inverses of each other. So let's go ahead and look at that. So here's your f of g of x. So I'm going to start with the f function first, 3 big parentheses, and then the 1/3 gets substituted in here. 3 times 1/3 is 1 times x is x. Then we're going to do gof, g of f of x. So we're going to start with the g function, which is 1/3 x. So 1/3 big parentheses. We're going to substitute the 3x into those parentheses. 1/3 of 3 is 1 times x is x. So because they both of those compositions equal x, 3x and 1/3 x are considered inverse functions of each other. So on this particular problem, we are to find the inverse of f of x equals the cube root of x plus 1. Then you need to determine whether it is a function and state its domain and range. So step 1, get out your calculator. And so if you get out your calculator, graph the function. So go to y equals, and you are going to, in order to get your cube root, you have to go to the math menu and scroll down, and your cube root is probably at number 4. Hit enter, and then put in x plus 1, and hit enter, and now graph. And you will see a graph on your window that looks like this. If your window's out of order, kind of out of whack, it's not your normal standard viewing window, you need to go to zoom and then scroll down to standard and hit enter, and then your window should look like this. So first of all, I need to determine whether it's a function. If I apply the vertical line test all the way through here, it is indeed a function. So the horizontal line test is also being applied here. So no matter where I put my horizontal line, right, all the way through here, it passes a horizontal line test as well. So note that both the original function and whatever its inverse is, they are both functions. So before I move to the next slide, I'm actually going to show you how to find the inverse function, because the next slide that I have is going to actually show you the entire math behind it. So I'm going to go ahead and move this up and show you the process. So the first step, I'm going to write my reasons next to my work, and then we'll go from there, but I'm not going to do this on every problem. So the first thing you're going to do is you're going to start with your original function. So f of x is equal to the cube root of x plus 1. So this is your given, if you will. Go back to your geometry. So then you're going to replace f of x with y, because remember that's what it means, cube root of x plus 1. So replace f of x with y. Then the next thing we're going to do is, so this is 1, this is 2, so then the third thing we're going to do is solve for, oh, I skipped a step, hang on. Then we're going to switch your x and y. That's kind of an important step. So then we're going to switch, because remember the inverse means that we're just switching the x and y. So then just these values get switched. So I get x equals the cube root of y plus 1. Finally, solve for y. So we have to have an equation that says y equals. So in this particular case, to solve for y, our y is imprisoned inside a cube root. So in order to get it out of that cube root, I'm going to have to cube this side because that will make the cube root go away. And what I do to one side, I'm going to have to do to the other side. So I get in x cubed equals a cube root raised to its same exponent gives you just what's underneath the radical. And then to solve for y, all I have to do is subtract 1, and I get y equals x cubed minus 1. And so then my final step would be to exchange f to the negative 1 of x for y. So then f to the negative 1 of x is equal to x cubed minus 1. And so you could check to see if you're correct by finding the composition of this function and vice versa. So if I were taking a test, I would actually find the composition of both of those, and they should give me x, and that would tell me that I did it correctly. So then the next slide is going to show you the math that I just went through. So here you can see that that's all the math that I just went through. The only thing they didn't do was replace the y with f to the negative 1 of x, which you should do. So because the inverse is a function, we're going to go ahead and graph that in our calculator as well. So you already have in your y equals, you have the original equation cube root of x plus 1. And that is this function here, this one here. Then I want you to put into your y sub 2 under y equals, I want you to put this in. So scroll down. And I want you to put x caret 3 and then get out of the exponent and put minus 1. Enter, and then graph. And you should see the second part of the graph coming through, which is this one right here. And the only other part that you're seeing is this line in this graph here. Your calculator won't show it, but this line right here is this is y equals x. And this line right here is the line that this graph is being reflected over to get your inverse. So it's just interesting to look that if I were to fold this graph along this line, if you had a little patty paper, it would fold, this part right here would fold right onto here, and this part right here would fold right onto here. So let's talk about the domain. So as you look at the original function, it's a cube root. I can take the cube root of a positive number, I can take the cube root of a negative number, and I can take the cube root of 0. So there's really no restrictions on the x. X can be whatever we want it to be, so it's all real numbers. And the same thing here, as you look at the inverse function, there is no denominator, there's no square root. I can put anything I want to in for x, positive, negative, 0. I can get whatever number I want. So both the domain and the inverse, both the domain of the inverse and the original function and the range of the inverse and the original function is all real numbers. Remember, we talked about this funky notation here, but I prefer you write it like this. Domain is equal to negative infinity to positive infinity, and your range is also negative infinity to positive infinity, and you can see that on both of these graphs as well. Then determine by composition whether each pair of functions are inverses. So I told you earlier that if you're looking at two functions, so we're given this one and g of x, it kind of looks like, I mean, we looked at 3x and 1/3 x and said, oh, and did the composition earlier in this video, and they both turned out to be x, and we're like, oh, they're inverses. So you see those happening again. Does +1 and -1 in here change anything? So let's go ahead and find those compositions. So I know that you see the work here, but I'm going to go ahead and write it so that you see me doing it piece by piece. So I'm going to find f of g of x. So I'm going to start with the f function, which is right here. So I'm going to just write 3x minus 1, but instead of the x, great big parentheses. So 3 great big parentheses minus 1. And then I'm going to substitute in to those parentheses the g function. So here we go. 1/3 x plus 1. Then we're going to use our algebra, and we're going to distribute. So 1/3, or so 3 times 1/3 is 1. So I get 1x. And then 3 times 1 is 3. So I get plus 3, and then minus 1. Combine your like terms right here. And then we get x plus, where did I get 2 from? That should be a -1. Sorry, my bad. -1. So 3 minus 1 is a plus 2. So that's our composition. Note that that composition does not equal just a plain x. So as a result, since it doesn't equal a plain x, I don't even have to do g of f of x. Why? Because both of them would have to come out to be x. So because it did not equal x, f and g are not inverses. There's no need to check Goff, g of f of x, if the first one you tried doesn't work out. No point in trying. Determine by composition whether each pair of functions are inverses. So again, they're showing you the work. It's a little bit complicated, so I'm going to go through it with you piece by piece. So let's start with f of g of x. Why? Because that's typically where we start. So f of g of x. So the f function is right here. So I'm going to write 1 over x minus 1 with great big parentheses where that x is. So 1 over big parentheses minus 1. And in those parentheses, I'm going to put this lovely gem right in there. So probably should make some bigger parentheses. So let me move that over here. Okay, so then I'm going to put in 1 over x and then plus 1. So to simplify, there's nothing in front, so I can just drop the parentheses. So I have 1 over x plus 1 minus 1. The plus 1 and the minus 1 are going to cancel each other out, and you're going to end up with 1 over 1 over x. Remember, if you have a fraction in any part of a fraction, you have to use keep, change, flip. So I'm going to keep the numerator. I'm going to keep this exactly as it is. I'm going to change this to multiplication and flip this to its reciprocal. So keep, change, flip. So keep, change, flip. Looks like KFC, but the C and the F are in the wrong order. So I'm going to keep my 1, which is the numerator, change division to multiplication, and take the reciprocal of 1 over x. So 1 times 1 over x joyfully is x. So f of g of x is x. So far so good. But then we have to test Goff, g of f of x. So I'm going to do g of f of x. So this time we're going to start with the g function, which is 1 over x, so big parentheses, and then plus 1 equals. We're going to put the f function in, which is 1 over x minus 1. Well, I've got to deal with the fact that this is a fraction and a fraction. So I'm going to do keep, change, flip. So keep times the reciprocal. So I've got 1 for my keep. Whoops, I want to change my color. So I got 1 times, so that's my numerator here, keep, change that to multiplication. I'm going to flip this to its reciprocal. So x minus 1 over 1, and then plus 1. So 1 times x minus 1 over 1 is x minus 1. And then we have a plus 1. And then the plus 1 and the minus 1 are going to cancel. And we are left with an x. So because both Fogg and Goff, the compositions, gave us x, then that means that f of x and g of x are inverses. So they are inverses. And this just happens to be the graph of both of those, if you put them into your calculator. And then they did not ask for the domain and range, so we're going to go on from here. So to find an inverse function from an equation, exchange all x and y terms and solve for y. So we already talked about that. So find the inverse of y equals x squared plus 3. So we're going to start with changing our x and our y to get equals y squared plus 3. So if I want to solve for y, I've got to get the y term by itself. So I'm trying to get that by itself. So subtract 3. I get x minus 3 is equal to y squared. Then I want to take the square root of both sides, and technically I should have a plus or minus square root on that side, because when I take the square root, I need a plus and minus. So y equals positive or negative square root of x minus 3. F to the negative 1 of x is equal to plus or minus the square root of x minus 3. So then the next question says, does y equals x squared plus 3 define a function? Well, if you were to graph it, it's going to look like a parabola. So go into your calculator and clear out anything that's in your y equals that we just put in there. And you're just going to put in x squared plus 3. And it looks like this. It is a parabola going through the y-axis at positive 3. So this clearly passes the vertical line test. However, so this is a function. However, the inverse, which we just found, it's not going to pass this horizontal line test at all, because you've got to put both that plus or minus square root of, what was it, x minus 3 in there, I think is what it was. And you had to put both of those in your calculator. So you put both of them in separate parts of your y equals. So if you put in y sub 2, if you put in the square root, I'm going to put in the square root of x plus 3, I'm sorry, x minus 3, enter, and then in your y sub 3, put in negative, and then the square root symbol, and then underneath there, x minus 3. You will end up with a sideways parabola going, so this is 1/2 of it. That's the positive square root of 3, and then this is the negative square root of 3. So it goes through the x-axis here at positive 3. And so as you can see, this is not a function. It doesn't pass the vertical line test. So, next question, find the inverse of y equals 3x minus 10. So I'm going to go through that. You can see the answer there, but let's go through it. So I'm going to start off with swapping the y and the x. So let's start there. So I get x equals 3 times y minus 10. Then we're going to solve for y. So there's your y term. We want to add 10 and add 10. So I get x plus 10 is equal to 3y. And then we want to divide by 3 and divide by 3. So that cancels, and I get y equals, and then you need to separate this. And you actually didn't have to. You could write it as x plus 10 over 3. So let's go ahead and write it that way. So you could write your answer as x plus 10 all over 3. And then f to the negative 1 of x is equal to x plus 10 over 3. That's a 10. So this is your inverse. And why are these the same as what you see as our answer over here? If I take x and divide it by 3, I get 1/3 x. If I take 10 and divide it by 3, I get 10/3. So these are both acceptable ways to write that inverse. Is the inverse a function? Well, let's see. This one would be easier to put in your calculator. I guess you could put this one in there too. But this is actually the graph of a straight line, because it's a linear function, mx plus b. So I can tell you it's a straight line, and it's not vertical because we're going through the y-axis at 10/3. But if you put it in your calculator, put in your y equals, take out all those three things that we put in, y sub 1, y sub 2, and y sub 3. And if you put this in there, you got to put this in parentheses. So x plus 10 in parentheses divided by 3, enter. It looks like a straight line like this. So that definitely passes the vertical line test. Then this is practice for you to find the inverse and the domain and range of the function and its inverse, and determine that the inverse is a function. If you want the answers, so go ahead and try this on your own. If you want the answers, feel free to take a picture of your answers and send them to me and ask me if you've got it correct. So good luck.